Hi, I'm Philipp. We're talking about zero-copy message passing today and how we implemented it in Dora in a way that we can share messages across different languages without copying the data and paying the costs. So we start with a short introduction to Dora, and then we talk about different ways of efficient message passing, and we'll focus on shared memory for communicating with a bit of background, like how this works with virtual memory and how shared memory is allocated on different operating systems. And then we'll look into Apache Arrow as a way to represent data in a language agnostic way, and also how to do some zero copy operations on the data. So the Dora framework is a framework for building robotic applications and also for AI. And it uses the data flow architecture. So we represent a program as a set of nodes which represent the different operations. So on this example on the right, we have a webcam node that takes images, and we have an object detection node that detects objects in an image. So each node has inputs and outputs, and these outputs are sent via messages to the next node. So the object detection node takes a webcam image as input and calculates the bounding box using some AI model, and then it's forwarded to a plot node that combines the image and draws a bounding box around the objects that were found in the image. And the advantage of that design is the isolation of the different components. So if the object detection node crashes, then the other nodes continue running, and you can restart the object detection, for example. And you can also split the data flow across multiple machines. So if you have a small embedded device that has no computing power, then you can put the object detection on a powerful machine and use the network to communicate the data. And you also have the option to add a new debugging node in there that just receives the messages and logs them for debugging later, or for tracing and replaying them later. And the motivation for Dora was that we want to provide an easy way to get started with the creation of robotic applications. So as a beginner, as a newcomer, you should be able to just check out the project and get started quickly without reading into build system stuff and so on. So we want to support various programming languages. First class support is for Rust and Python, but we also support existing C++ code. So if you have some Rust 2 code or so, it should not be too difficult to migrate that code. Just use a different API, hopefully. And but the rest of the code can stay the same. And we have also plans to add support for WebAssembly nodes, as a form of additional isolation, because WebAssembly is also sandboxed again. So if you have something safety critical, then you can really isolate that part. And one goal was to keep the build system as simple as possible. So we try to use the standard build system of each language if possible. So for Rust, that's cargo. For Python, you have something like pip. So you can also use external packages from crates.io or something, which allows you to reuse lots of code. And the data flow then is defined through a YAML file with a simple configuration where you just specify the nodes that exist and which output and which input are mapped to each other. And one ongoing project is that we have a node hub, a collection of common nodes for example, for recording data from a microphone or webcam, or for some AI models that are commonly used, for example, some YOLO object detection model or something. So again, to get you started quickly, and then you can fine tune later if you like. So since there's a lot of Rust 2 code in the wild, so we also try to provide a bridge for existing Rust 2 code. So the idea is that you can migrate your existing data flow part by part. So you have the option to only migrate a single node, for example, to Dora, and then they can still talk to each other, because we have a middleware that interfaces at the DDS level. So you don't need to use the ROS2 build system to build Dora, or the other way around, but instead you can build them separately and they still talk to each other via DDS. And we pass the ROS2 message files of your project, so you have like all the message declarations auto-generated into Rust and C++ bindings, so you got autocomplete and you got type checking and so on. And we also provide automatic type conversions, mostly for Python, because Python is not able to like represent all the differences in types that Rust2 expects. So in Rust2, in DDS, like an object is represented, like a struct is represented in a different way than like a map, but in Python they're kind of the same. So you have to do an automatic conversion to the expected type so that the Rust2 receiver will take the data and not ignore it because it's invalid. So let's talk about efficient message passing. So we have in Dora inputs and outputs, as I mentioned, and each node is a separate process from the like system architecture. So we have isolation and fairness because the operating system can just do the normal scheduling. And we also have like a high degree of flexibility because like each node is a separate process. So you have full control over the process. You have your own main function. You can call into libraries. You can talk to the hardware, whatever. You can do that without affecting other nodes. But that involves some challenges when it comes to communication because you don't have any common memory. So there are, maybe quickly, this is the YAML file, how you define inputs and outputs and how you map them to each other. I think we even simplified the format a bit to like reduce one level of nesting, but that's like the base. So the question is, what's the best way to pass messages between nodes? So you have like TCP sockets, which are nice. They are cross-platform, they're standard. You can access local, you can access remote machines. But compared to like shared memory or like Unix IPC, TCP can be a bit slower because it has various sources of overhead because like it always has to deal with like network in unreliability, which we don't have on a local system. So Unix IPC has also advantages. It's faster, but it's only available on Unix, so it wasn't really a good candidate for our framework because we also want to run on Windows, for example. So shared memory is like a good way to like speed up communication on the same machine because it's cross-platform and you can really do zero copy operations. You put the data in there and the receiver takes the data out. So in Dora, we use a combination. We use shared memory for local communication, and if the receiver is on a remote node, we use TCP sockets right now, and we have plans to switch that to Zeno because that's a bit more flexible and also supports different network topologies. But yeah, what's shared memory? Like, how can we share the data using shared memory? So the idea is that we have a region of memory that is mapped into two different processes or even more processes. And that works through virtual memory. Virtual memory is an abstraction that almost all operating systems use today, at least the higher level ones, and embedded devices, they might not have them. But the idea is that each process has its individual address space, and it can only address that address space. And the hardware has a memory management unit that translates these addresses to physical RAM addresses. And this is completely transparent to the individual process, so the process doesn't see that, and it cannot even see which other processes are running on the system because, it only sees its own address space. And that also means that, like, if there are no side channels, hopefully, then you cannot read the memory of any other process on the machine. You also have the advantage of portability because you don't need to deal with like hardware details, how much RAM is available, which regions of RAM are like reserved for graphic cards or some other connected devices. So that's all for the operating system to deal with. And the operating system can also use that insight and that power to like do efficient memory management. So it can reduce memory fragmentation, swap parts out to disk if the RAM becomes too full, or it can do some lazy allocation where if you do allocate a big chunk of memory, then the operating system does nothing, and just only when you access it, then it really selects some RAM memory to back that memory. Yeah, and shared memory works by making the MMU map the virtual addresses of different processes to the same physical region in RAM. So it looks like normal memory to each process, but actually behind the scenes, it's the same memory that another process accesses to. And that means you can access it without any communication overhead, and you can share data this way if one process writes data in there and the other process takes it out. But you have to be careful, of course, because like if both processes write something at the same time, you easily get a data race and undefined behavior. So you need a clear protocol of like who's sending and who's receiving, like similar to like an unsynchronized bus or something. So, and if you want maximum performance, you also need to think about cache invalidations. So if you write in an alternating way, then you can easily get a situation where the data is always removed from the different CPU caches at the core level and needs to be reloaded from memory. And that can lead to decreased performance, especially if you access the data often. So yeah, maybe just a quick slide about how you use that shared memory. So the idea is that you back them by a file descriptor, I think on Unix and on Windows. So you allocate a file descriptor that is associated with that shared memory region, and then you map that region into your address space. And after doing that and writing some data, you can take that ID, that file descriptor, and send it to the receiver. You need to use, of course, a different communication channel there, and the receiver can also map that data then. Quick code example in Rust. So in Rust, we have then the nice shared memory crate, which abstracts the platform differences away, but it does essentially that. So we first create a shared memory region with a certain size, and then we write some data in there, and then we get this OS ID, which is like the file descriptor ID, and can send it to different process, and process B is the receiver in this case. After receiving the ID, they can map it into their own address space and read the data. So like if you implement a message passing algorithm on top of shared memory, you need a way like the sender writes the message and the receiver takes it out, and it's good to avoid allocating too much. So because the allocation has some overhead too, so it's good to reuse the shared memory region if possible for the next message, but that needs some back channel. So the receiver needs to report back once it's finished with the data. Otherwise you are never sure when you can write or if the data is still in use. So for Dora, we have like a back signaling channel that sends a token that describes which area is now reusable again. And as another optimization, we also send small data via a local TCP channel because the overhead of allocating a shared memory region would be larger because it's like page size minimum. So you also have like a minimum size of the message, and that overhead is higher than the overhead of TCP. And in general, when you deal with with shared memory, you want to do lazy operations. So you want to avoid taking the data, calculating something, and writing the result to the heap, because then you copied the data. And if you want to send that out again, you need to copy it from the heap into your shared memory again. So the idea, like it's preferable to, if possible, do lazy operations which have no effect until you write the data out at the very end. So you can stack multiple operations and then write the resulting data directly into shared memory. And then the receiver of this next message can read it directly again, and you have no copying of the data without modification. So using that approach, we can share raw byte data. We can write some data in there, and the receiver can take the data out and read it. But often we have like structured data. So we have string data, object data, and so on. So the data needs to make sense, and the receiver might use a different programming language than the sender. And that can be a challenge because, for example, string data is represented very differently in languages. And string data is a very basic type, right? So in C, you have like a null terminated ASCII string, ASCII byte array. In Rust, you have an UTF-8 array, which is not zero terminated, but instead you store a separate length. And in Python, you store strings as string objects, which contain additional metadata, for example, a hash value to give like the Python runtime options to like deduplicate strings and so on. So there's no way that Python or like C is able to read a string that is represented as a Python object. So instead, we need to have a common data format to represent the data in a way that is compatible with all the languages that we want to use. And that's where Apache Arrow comes in. So Apache Arrow is a cross-language data format which supports a wide list of languages, like including Python, Rust, C, C++, and so on. And also is very flexible in the amount of types that are representable. So you can, almost all Python objects can be represented in a way in Apache Arrow, for example. And yeah, maybe one point that's not on the slides, it's not like a serialization framework. So you don't take the data and encode it in a way like to JSON or something and then decode it again. But instead you really work with the data, so you don't need an additional copying. And Arrow data is also immutable by default. So you never need to worry that the data might be overwritten by someone because you can only copy it, you can never modify it in place. And the whole data format is designed with like lazy operations, zero copy operations in mind. So the format itself is like the memory is arranged, the data is arranged in memory in a way that enables lots of operations already. And it's also directly compatible with the NumPy and pandas format. So you can, in Python, simply plug it into a NumPy to do some advanced processing without an additional conversion step. And one additional advantage of immutable data is that you don't need to think about data races, because data races only happen if you modify data. So this yeah, solves the issue that we have with shared memory. The basic type in Apache Arrow is an array. So here we have an example of an integer array. We have the values 1, a null value, 2, 4, and 8. And this is represented as an array with 2 buffers. So buffers can live anywhere, so they can also live in shared memory. And the value buffer, the second one, that contains the actual data. And then we have like an additional bitmap, a validity bitmap, that specifies which values are valid. So this allows you to like delete individual values without modifying the underlying value buffer. So this is like a zero copy deletion operation because you can very cheaply clear values from the list. And you can also nest arrays to create more complex types. So you can like create an array of lists. And for that, the data format would be that you have like a child array that contains all the integers without any separation. And then you have like an offsets buffer that specifies the start address and the start offset and the boundary offsets. So the first list starts at offset 0, and the first boundary offset is 3. So first array goes 0 to 3. The next boundary address is 3 again. So the second array goes from 3 to 3. So it's the empty array, and so on. Yeah, and one central design aspect of Arrow is that it's column oriented. So if you have a struct with multiple fields, you don't store them first first struct instance, then the second struct instance, but instead you take each field and store it as a separate list. So in this example, we first store all the integer fields in a list, and then we have a second list with the string fields. And that enables, for example, SIMD operations for faster processing, but it also enables you to do zero copy operations. For example, if you have like a processing function that takes in a list of integers, you can just take that and ignore the list of strings, and put that in, and you don't need to change the data in memory in any way. Structs are represented, like as I said, as individual lists of for each field. So in this example, we have like an array of structs with a string field and integer field. And I don't know what's with this rendering, but the first child array is containing the string data. Again, we have a value buffer that contains all the strings bytes. And then we have an offsets buffer that specifies the start offset and the boundary offsets, where like the next string begins. And the second field is just an integer array, simple and easy. And the nice thing about that format is, for example, you can even add another struct field in a zero copy way. So if we want to add a Boolean field to the struct, then we just add a new child array. So only the outer wrapper changes, but the child array for the first field still points at the same data, and for the second field the same. So these can still point at some shared memory, and we haven't really copied the data, did anything with the data, and we can treat that as a normal array and pass that on to NumPy also on, or like do some other processing on it. Yeah, and using Apache Arrow is, as I said, possible from lots of languages. In Rust, we have this Arrow crate, this official one. So Arrow array is like a subcrate of that. And there you have like types for all the different array variants. So int32 array is like an int array of 32-bit values, and you can construct it from an iterator. You can construct it from like using the builder pattern and append the values one by one. And you have like slicing methods, for example, for taking a subslice of your array, which are also zero copy, of course. And in Dora, we also have like convenience functions for conversions, like you have the try from implementation from this general arrow data type into a byte slice. So you can work easily with arrow data coming in as input and then treat it as like a Rust type and use normal Rust processing functions. Yeah, and in Python you have the PyArrow library, which is also quite straightforward to work with. And as I said, you have these zero copy conversions to NumPy and pandas, which don't require any additional conversion. And since the Arrow data format is completely language independent, it doesn't matter if the sender of that data was a Rust node or a Python node or a C++ node or WebAssembly node. The data looks the same, and you can still communicate, and you can treat the data and process the data without any intermediate copying. And that is leading to quite some good performance. So in this graph, we have the latency compared to Rust2, which also supports shared memory as a communication pattern, but not for Python nodes. So this is like the extreme comparison where Dora is able to use shared memory because it's a Python node, and we also support shared memory for Python, but Rust2 doesn't. So you see that for large messages, the latency is much bigger for Rust2 than it is for Dora. Yeah, and that was my talk. Thanks a lot for listening. And yeah, if you want to know more about Dora, Xavier had a talk this morning, I think, at the Embodied AI track. I think there's a recording. So there you can see he had like a robotic arm that is like used with Dora. So